I work on embedding method, and what I will tell you today about is motivation between quantum embedding methods. This will be very general and is not meant to be fully rigorous and mathematically correct. It's just meant to give you some sort of motivation, what we are trying to do, why these directions are important. And I know that after me, Lynn is speaking, and I'm sure that his talk will be fully mathematically rigorous. This is like point of view about embedding given by, you know, somebody who is more on the physics or chemistry side, how we think about it. So one of the most important things are physical consideration, why we would even bother to, you know, to deal with embedding methods. So imagine that we have some sort of huge system, right, which obviously would be extremely difficult to compute brute force at a very high level of accuracy. So the truth is that there are many such systems that are interesting for us in chemistry and physics. And even if we threw all the possible resources that we have at DOE or NSF, clearly we wouldn't be able to, you know, to arrive to a brute force answer that has a very, very high accuracy. So clearly some sort of idea to circumvent this problem would be needed. So if we analyze many of these chemical or physical problems, how they look and how the electrons behave in them, one can see certain characteristics. So in some of them, we may be interested only, for example, in molecule that is embedded or surrounded by water. In some other, we may be interested in a molecule or really even only in a couple of transition metal atoms that are absorbed on a surface. In yet another problems, we may be interested in metal organic frameworks, but, you know, indirectly when one would search for this motive that is of physical or chemical basically impact, that would be, for example, transition metal atom that is a linker and to which maybe carbon dioxide can absorb, or, you know, other chemical reaction can happen in that way. Basically, when there are other problems, right, also more of biological significance, when we can study, for example, DNA type of base pair stacking, right, and one is only interested in this type of interaction energy, but not what is happening to the surrounding, really. But one of, you know, the problem that is most dear to my heart is basically the study of solids and what's happening in the D or F electrons of solids. So even though the whole solid, like the solid pictured here, which is cuprate, can be extremely complicated, the truth is that what one is interested in, like for the physical significance of this problem, are really these plaquettes, right, of the copper d orbitals. So in each of this problem, even though the problem itself looks extremely complicated and, you know, generally not tractable in its entire form, but methods that are maybe post-DFT have very high computational scaling. But in all these problems, we are only interested really in some specific fragment that is responsible for physics and chemistry. So what that means is that there is some natural simplification that may be a result of this interest of only in a part of the problem, and that the whole problem could be mapped into a problem of basically solving system that is embedded in some kind of environment. So this by itself is not yet a simplification, right? Because we just changed the description of some problem that is generally computationally intractable onto two separate problems of description of a system that is embedded in environment, and most likely this environment also would need to be described at certain level of theory. So from like the absolutely top point of view, the embedding procedure changes one difficult problem onto two difficult problems, but perhaps we would assume that they're more manageable to general calculation. So our question would be, how do we describe system and environment? So see, all these embedding problems, like what I showed you, are basically not created equal, right? They have some certain differing characteristics that I'm sure if you are a chemist or physicist can feel. So what is happening in some of this problem, like the system that is interesting is more or less basically embedded in something what is like electrostatic charges. And in some other systems, like for example, this cuprate, we don't really have this definitive separation between what we would call system and environment, right? Like here we can say this sort of molecules that are this ball and stick molecules are clearly probably a little bit different than what is pictured as this helical ribbons, right? We don't have the same type of differing characteristic for these d orbital planes. So what that means that basically this forces us to choose different ways of solving these embedding problems, and that this chosen fragment has to communicate with the environment in a different way. So basically, there are easier and more difficult embedding problem, and this easier problem usually would be based on what we called quantum mechanics in molecular mechanics embedding. So there we can assume that this chosen fragment is basically embedded into field of classical charges. There is no electronic exchange between the system and environment, and the wave function of basically the system does not need to delocalize in any significant way to the environment. So these methods, right, like which rely on these assumptions are called quantum mechanics in molecular mechanics embedding. They're well understood, and up to now there has been a lot of progress. That doesn't mean all the problems were solved in that field, but I would say like the general framework is pretty well understood what to do. Then see, on the other hand, there are these problems where we really are having a system that is dense, where we cannot truly, separate the system from the environment and say there is no electron exchange between the system and environment. So this type of problems are solved in what we call quantum mechanics, in quantum mechanics embedding. So this chosen fragment is usually embedded in some kind of dynamical mean field, which is frequency dependent. And that allows us to describe the electronic exchange between the system and environment. This whole procedure, right, has to be designed for what we call open system, because basically the system exchanges, right, electronic charges and electrons with the environment. The wave function has to be able to delocalize. So see, this quantum mechanics in quantum mechanics embedding methods, they undergo very intense development, and in my talk, I will tell you about the major, basically, types of these methods. I will focus on one type. I will focus on Green's function methods, but I hope that I will give you significant background that you will be able to generalize that and, think about what's happening in these other types of embedding methods too. So basically, why solids are good candidates for this embedding method. So imagine why we cannot do brute force in solid. Like, it's kind of self-explanatory, but just to give you exactly, this flavor why we cannot do it, right? So imagine that we have a unit cell in a crystal, and obviously, we have some number of orbitals in this unit cell, let's say n. So the question is, in order to describe a material, right, in this regime, how many of these unit cells you would need to treat explicitly? How many you would need to treat fully brute force? So in order to avoid major finite size effect, right, we would need to extend this solid in all directions, if it's like a 3D type of material, until basically the interaction between the central cell, right, and the distant cell decay appropriately. So that means, right, we would have an X and Y and an Z cell in each direction. So that usually means pretty many cells, cells in like the most modest cases, at least 4 cells in each direction, right? And even the simplest perturbational theories that could be applied, like MP2, would scale basically as n to the 5th times n4th, right? So if I have 10 orbitals in the unit cell and basically 10 cells in all direction, you can immediately see that this would be extremely high cost. So even the lowest cost DFT method would actually be very computationally expensive. And not only in solid, we have this complication that it's computationally expensive, right? That maybe we could even beat. The problem is that we have different types of electronic behavior on top of that. So if you look at this oxide perovskite, for example, which is lanthanum titanide, and we would visualize orbitals in the unit cell for the system, right? We would have these p orbitals, and the same is for s orbitals. They will stick out of the unit cell. They will be fairly delocalized. And electrons in them actually have very high kinetic energy and low potential energy. So it means they can delocalize fairly easily and will result in uniform electron density. So they are kind of wave-like and can be easily described by methods like DFT. But when these D and F electrons, right, they centered around nuclei, they spatially confined, and because of that, electrons in these orbitals, they have to very strongly avoid each other, right? And this strong avoiding each other give rise to what we call strong correlation. And these electrons are basically very hard to describe by current method. So clearly, if we wanted to describe, both types of electrons and have a very advanced numerical method, like some sort of exponentially scaling method, this is absolutely inaccessible for any solid state or even larger molecule. So this is why we are interested in this embedding method. So just to, drive this point home, why basically anybody looks at these embedding methods, right now. So imagine that this is a graph where we would picture system size versus the degree of electron correlation of different systems, and we would ask how different methods in quantum chemistry can describe this type of problems. Right, so for realistic solids, we could run Hartree-Fock, we could run DFT, some low-level perturbation theory. And that means that this is not extremely correlated regime, right? This is where the correlations are small, the results will be good. For small molecules, we have actually very many methods that we could run in, weak correlation regime and both strong correlation regime. They will give very good quantitative answers. But see, if you look, this sort of corner, right, is not covered. So this is basically where most of these embedding methods are designed to be applicable, right, when the correlation is strong and the system is big, because we cannot use this traditional quantum chemistry or condensed matter methods in basically this corner. So, can we run it anyway, even though we said it's not applicable? So just to show you for this common insulator, which sometimes I call mod insulator, like nickel oxide, iron oxide, simple LDA, for example, density of states would predict that basically the state has, like the nickel oxide has a band gap of 0.2 eV, that would be the prediction, while in fact the experimental band gap is close to 4 eV, right? So some sort of low-level DFT would not give us correct prediction for this type of problem. So clearly, if one wants to run some post-DFT methods, right, it has to fall into this category of possibly embedding method due to the possible cost. All right, so what kind of methods people worked on for this open system? So these methods differ by basically object used in embedding, right? So one can use wave function, one can use the density matrix, and one can use Green's function. So see, in both wave function and density-based approaches, usually they are targeting ground state energy. They usually executed at 0 temperature. One can get, for example, lattice constants, so optimize the geometry in them. One can get on-site occupations. In the Green's function methods, one targets usually naturally a little bit different quantities, like photoelectron spectrum, angular momentum resolved spectrum, or one targets temperature-dependent quantities like specific heat, Helmholtz energy, entropy, and so on, basically like thermodynamic quantities. But one can also get band gaps, ground state energy, one can get very similar quantities to basically the wave function or density type of quantities. So the major difference between these different embedding methods, right, is that in basically Green's function, we are targeting spectroscopic quantity and thermodynamic quantities like Gibbs energy, specific heat, susceptibilities. And here one targets usually ground state type of quantities. So if we would kind of talk about all these varieties of embedding methods, and I could give some examples, right? So for example, wave function embedding is like a density matrix type of embedding designed by Garnet-Chan. When the embedding based on density, these are usually like some DFT types of embedding designed by Tomek Wesołowski, Emily Carter, Tommy Miller. They usually target the ground state or almost entirely target the ground state via temperature independent. On this sort of side of Green's function embedding, there is dynamical mean field theory embedding designed by Gabi Kotliar and Antoine George. There is self-energy theory embedding, which I worked on. These are the major players. So basically, right, the major difference is what object is used to describe system and environment, and then depending on this object, one can evaluate different quantities for different experiments, either at zero or finite temperature. So what does experiment want if one wants to cover solid in this embedding? So if one wants to cover molecules, obviously the experiment wants something different, but I will focus here on solids because I think that this is where the embedding has the biggest possible splash. Actually, the molecular examples are, I would say, fairly well covered at present. So see, in solids, what people usually, like they don't want the total energy usually. So this is not like for molecular problems, right? Because to get the total energy of the unit cell, it would mean that this is cohesive energy of the unit cell. So one would need to somehow decompose the energy, the unit cell onto atoms, right? So that's kind of like a very messy experiment. But what people measure usually for solid is angle resolved photoemission spectroscopy. So what happens? One has a photon source, there are photons incident on a sample. They eject the electrons from inside of the solid. These electrons are caught into basically energy analyzer, which analyzes their both momenta and energies, and that gives rise to the band structure and the bands that we see. So more or less, if you imagine that we are, I don't know, bombarding a copper surface with photons, right? It would eject for us the valence electrons, and we would catch them, register their energy and momenta, and that would give us basically such simple picture. So this is one quantity that one would want to know, right? When one can read off the band gap and so on. And of course, this is, very simplified, right? So if we would, let's say, take molybdenum selenide and the GGA band structure, we would get something like this. But the truth is that, experimentally, when one does ARPES, one sees sometimes more complicated electronic structure than DFT gives, right? So this is like an example of ARPES for this molybdenum selenide. One sees certain broadening of the band. This is not necessarily due to temperature. Some of them is entirely due to actually correlation at the post-DFT level. So this is right what preferably such embedding method should be able to give you if you want to compare with these experimental quantities like ARPES. Then what else people may want for solid, right? They may want to get a phase diagram as a function of temperature and hole doping, for example, or as a function of temperature and pressure, right? And one can argue how the material scientists who are experimentalists may want to get it, right? But they usually want to know the explanation of electronic behavior in these different phases. So basically, they may want to know how the electrons are localized on certain metallic centers, what are the spins of the center, right? If this is like some more covalent system or very significant charge transfer and so on. They may want to do that as a function of different parameters to create this phase diagram, right? But one thing they may want to have it completely material specific. So see in, for example, traditional condensed matter, one can create all these diagrams, right, as a function of some kind of parameters that enter this Hamiltonian, let's say U and J. And when one sees that the phases are appearing, but that not necessarily means for an experimentalist that if I substitute this atom or if I, change my length of the bonds by some sort of, right, like different substitutions that will make me go to that phase or go through this phase transition. So I would say in the most accurate limit, you may want to have a completely material specific simulation. So there are other quantities that one may want to get from experimental point of view for the system. So for example, if one has like a complicated metal organic framework or some kind of molecular magnets, what one usually wants for this type of system are spin correlation functions or temperature dependent magnetic susceptibility, which basically tells us, right, like when we applied field as a function of temperature, how the spins on these metal organic centers are flipping. So these are the common quantities I would say one would want to evaluate for large molecules like metal organic framework, molecular magnets, or get from for solid state. So this makes it clear, right, that for example, in molecular problems, one of the major expectations to evaluate, right, or major expected quantities to evaluate is energy. Here, the energy is very important. It can be evaluated, but usually some sort of byproduct of this calculation. And we are looking to really get this type of thermodynamic quantities. So these thermodynamic quantities, see if they can be gotten from Green's function, and Green's function are very natural language. So, like the beginning of this Green's function language can be basically dated to some of the summer symposia in theoretical physics that happened in Michigan, in Ann Arbor, in basically early years. So one of the first arrival who talked about, this sort of Green's function language was Schwinger. He gave a series of such workshops and colloquia for students in 1948. And this is one of his, actually, I think his very first presentation of this type of language was during this summer school. So even 1 year later, Richard Feynman gave basically his version of QED, right, in 1949, when it already contained diagrams, right? Schwinger only gave formulas. Really, it was more analytical, not diagrammatic. And then in 1950, Dyson gave, again, a summer school where he understood that these two approaches are equivalent, and basically this is just a different representation of the same quantity, one through diagrammatic means, the other through more explicit analytical means. So in these Green's function approaches and in these types of embedding, we use this type of language. So, what are the challenges, how this language evolved, and where this embedding method fall into the development of this language. So see in 1950, right, early 1950, there was QED was developed. Then in 1960, there was a general functional that governs Green's function, I would say mathematically established by Latinger and Ward. And then in 1965, Hedin wrote his GW. So the G0W0 was used from 80s onwards for treating very large problems, right? And in 1992, dynamical mean field theory was introduced for model Hamiltonians. So this is, I would say, I would say that this DMFT step is the beginning of embedding theory that is expressed in the Green's function language. So these were all finite temperature approaches. When DMFT is again explicit finite temperature approach, what we still actually are searching in this embedding approaches up to now is for basically like a fully ab initio theory for strongly correlated solids without any adjustable parameters. And this is the same goal as for actually all other embedding methods. So if you make it based on density or wave function, I would say this is still a valid question in all these theories. So why this progress was slow, and why it took so many years from the introduction of the language to really getting where where people are right now. This is, I would say, because the problem is very big. So requires both, I think, like joining strength between mathematicians, I don't know, physicists and chemists. And I would say that initially, most likely just the model system could do it because the experiments were not that sophisticated. And even if, even if the experiments were sophisticated, the truth is just that there was no computational power, I think, to evaluate a lot of these things. So this Green's function approaches and embedding method, right, they have to describe open system. And in this language, we basically have many choices how one can do it. So the Green's function, in the same way as wave function, can be written in time-dependent language. And when they are used to study problems out of equilibrium. So we will not deal with that in any way, in today's exercise. What we will focus on are time-independent Green's function. They describe a stationary problem at equilibrium. And basically, they can be expressed on two axes, either real axes, and when they are used to evaluate basically the spectra. So usually they will be used to evaluate like photoelectron spectrum. Or they can be expressed on imaginary axes, and when they are used to evaluate thermodynamic quantities. So they can be used to evaluate energy or Gibbs, like internal energy, or Gibbs energy, specific heat, and so on. So we will focus only on these two branches today as used in the formalism, but we will mask it so you are not scared by any of the equations, but you still can get the physical sense of what's happening. So in this time-independent Green's function, like one of the simplest Green's function one can write is the Hartree-Fock Green's function. So this is basically just like you can think about that as inverse of the Fock matrix in some way, right? Given on the frequency axis. And the other wave function that one can write is the full correlated, full configuration interaction or exact diagonalization Green's function. So basically, this is like a equivalent to evaluating basically the inverse of the Hamiltonian or diagonalizing the Hamiltonian. But there is a quantity that joins this two Green's function, which is called self-energy. And basically, this self-energy describes all the correlational effects that are present in a many-body problem. So all many-body effects that happen within a given molecule or solid. And it's evaluated as difference of inverses of this Hartree-Fock and correlated Green's function. So for better or worse, you can think about that as some sort of frequency-dependent correlation energy that, that is given. And in all these Green's function approaches, our major, I would say, mathematical task is to find the approximations to the self-energy by some means. So what is important, right? If some Merlin gave us the self-energy, we would know about all many-body effects present in that system of interest. So, of course, we're not going to get it exact, right? So our task is to find approximations. So this Green's function, right, are expressed on this grid or contour. So this is basically this omega. And the real axis Green's function, right, they have poles above or below the real axis. And they are, right, these poles are really the peaks in the photoelectron spectrum. The imaginary Green's function, right, has poles along the imaginary axis. And this looks very different when photoelectron spectrum. These are very smooth functions. So usually in computation, we use this imaginary Green's function because one can iterate easily with them. They're very smooth objects, you know, they don't have this type of jagged features like the spectra. So if this Green's function area interests you in any way, I would say from, you know, maybe even from historical point of view, I really recommend this paper in which actually the Latinger and Ward for the first time derive very precisely Green's function by studying partition function. It's actually quite enlightening how they do it, and I think very rarely presented in the book that way, but it's a wonderful historical perspective. So I deeply recommend this paper. And when they arrive to the notion of self-energy and Dyson equation, they study diagrammatics, right, where they basically say that the total Green's function, the correlated Green's function, is connected with the non-interacting Green's function by the usage of self-energy, which is the subject which describes all the many-body effects. So the question, right, as I told you, is how to find this approximate self-energies. So the good news is that from mathematical point of view, for this Green's function, we have a universal functional. So this functional is called Latinger-Ward functional. It's a finite temperature functional. And this functional can be used to get grand potential. And this functional is completely in some way analogous to Hohenberg-Kohn functional at zero temperature. It also has this sort of, it's universal, right? And from the Latinger-Ward functional, you get grand potential, right? From this Hohenberg-Kohn functional, you get grand state energy. So of course, the kind of major difference between Hohenberg-Kohn functional and the Latinger-Ward functional is that the Latinger-Ward functional has an explicit way of constructing it. So we know that such functional is created as a subset of skeleton diagrams present in exact functional. So in this right diagrammatic approach to QED that Feynman is using, one can draw all these diagrams, and one may not be able to evaluate them, but one can draw them. And then one can, choose subsets of the skeleton diagram, right, and construct this sort of approximate functionals. So one can construct approximate functional for methods like GW, methods like MP2, and so on. And this functional is connected by functional derivative to a quantity called self-energy. So basically a functional derivative with respect to Green's function of this functional is called self-energy. So you can see that there is a clear analogy, right, between Hohenberg-Kohn functional and exchange correlational potential. So right now, right, the question is how do we find approximations that are viable computationally to this functional? So just one more thing, this functional, right, is a functional in this original design of Green's function and Baire interactions, Baire-Coulomb interaction.
Dominika, can I ask a question?
Yeah, sure.
So for the MP2, is that MP2 or GF2? So the Green function lines, they're both, no?
So it will depend how you subtract here and if you have bold lines, right, or not. So I'm taking this exactly from Robert van Leuven, and I think that he defines this basically lines with the prefactors here as MP2. I think for GF2 we would have slightly different, it would be, I think, 1/2, and the line is not bold.
Right, that's the von Bath paper.
This reference here.
Yeah. Uven and one bar. That,
yeah.
Yeah. But indeed, for any MP2, you need to replace by the skeleton, not the skeleton lines. That's just the bare diagram, right?
Yeah, yes, for MP2, you don't have any renormalization of lines, basically.
So it's kind of weird that they call it MP2.
Yeah, I don't know why he does this. Like, see, I kind of write, so this is exactly copied from that paper, so I didn't change it, but I would say you could define this functional without renormalization when it just does not fulfill certain sum rules, right? So in principle, I think there is nothing wrong with defining functional without the renormalization of these lines.
Yeah, just to clarify. Thanks.
Dominika, can I ask a question?
Sure.
Have you thought about what the domain of the Luttinger-Ward functional is?
So this is very interesting question, actually. I think that, many times this, I think historically these domains were not very well studied. And for example, there are many papers about like non-physical solutions and so on. And I think within the, like the kind of mere practitioner, not like me, not mathematicians, right? We would, some of us, like me, for example, and Robert van Leuven, would think that, these wrong solutions arise because the domain was not properly defined, like some other, probably like Lucia Reining would tell you that, no, this is not true. But I think this is a very good mathematical question, actually. And I think all our community would really welcome involvement of, sort of people who are properly trained, not just kind of mere practitioners of who are using Green's function. So the domain is, I think, for many problems, an open question here.
Okay, thanks. But Dominika, but your answer, you have a more concrete answer, right? The thing that you and Manuel Go have been advocating in recent years, and which is this Nevelina and also its generalization. Do you think that's the answer, or it's not enough?
I would think that one could even restrict it further. So this only came within like last year, right? But I would say before that, I think there was no like general answer about the domain. So, but even I think the Nevanlina, my guess is that even that could be improved by somebody with proper mathematical training.
What we don't know is whether Nevelina is enough to make the Luttinger-Ward well defined. That seems to be definitely kind of open.
Precisely. So, all right. So when one does embedding in this Green's function formalism, right? So the first question one wants to answer is how to find good approximate self-energies. So, so one approximate this functional, right? And one can do this approximation doing this embedding type of concept. So one of the simplest, right, approximation that one can figure out basically to do in that way is that one, let's say, has some sort of physically interesting problem, and one divides this problem onto the system and environment, and this division is truly defined, by taking some kind of physically relevant fragments. So one calculates the environment at the lower level method and the system at the higher level method, right? And the separation is truly done based on some kind of, let's say, that one treats only d orbitals as the system and the rest as environment. So then, ideally, this functional would separate onto some sort of low-level functional for the full problem, right? Some higher level evaluated functional for this chosen system, and some double counting correction, which again is low level functional for chosen system. And since the self-energy in the most correct form of this Green's function approach is the functional derivative, right, the self-energies would follow the same trend. So I want to stress that this should be treated as some sort of general prescription. And even for a method that may not fulfill what we call phi derivability, which means that the self-energy may not be, precisely defined as the derivative of the functional, one could still imagine that one could write, for example, some method in terms of some of the self-energies, even though there may be no directly corresponding Latinger functional that can be differentiated in that way. So treat this as general, treat this as two kind of not necessarily related equations. All right, so how does this translate into solid? Right, so in solid, obviously, we have this infinite system that is intractable by some high-level method brute force. We usually are interested in properties of the unit cell, right? So we would assume that we are interested in the property that is local enough to the unit cell, that it's enough for us to cover the unit cell. Maybe, and then we would repeat this answer in each direction, right, or for each k point. And if this is local enough, it doesn't show enough variation with respect to momenta points that this distribution would be correct. So this is basically like a major idea of what was introduced in 1992 by Gaby Kotliar and Antoine Georges for dynamical mean field theory. And basically what they showed is that for Hubbard model, they can, in infinite dimensional limit, they can basically write a functional, which is a functional of Green's function and DMFT functional, as sum of the functionals of strongly correlated subsystems. Basically, for strongly correlated subsystems, with this assumption that the interactions are truly local to the subsystem. So basically, our assumption is that the Coulomb interactions are only on-site interaction and truly local within a subsystem. The subsystems are only joined by what is called hopping, which is just kinetic energy terms. So, of course, this is very good for Hubbard, but in realistic system, right, this doesn't truly hold. And in realistic system, we have not only the on-site interaction, we also have inter-site Coulomb interactions, and they usually don't decay that quickly. They actually decay fairly slowly. So we had very complicated hopping, but that is not a problem actually, but we also have this Coulomb interactions between all sites. So the early answer to that basically there are all these different non-local interactions, non-local because they not just contained within this kind of system or site, was a method called LDA plus DMFT. And in this LDA plus DMFT, the assumption was that we're going to treat the whole system at at the LDA level, or Hartree-Fock, that also would be classified really as LDA plus DMFT. And so we're going to have some sort of low-level functional, right, for Hartree-Fock or LDA. And that will describe for us all these non-local interactions, while the local interactions still will be described by some kind of high-level method. And we evaluate these functional pieces from this high-level method, right, and we subtract the double counting. So I'm talking in these very abstract terms. I will then try to make more precise how we can evaluate these pieces of this functional or self-energy. And see, so LDA plus DMFT, this really was developed by very many people. It caught up enormously in this embedding field. So by Gabi Coltiar, Antoine Georges, Andy Millis, Sasha Lichtenstein, really very many methods. I mean, very many people were developing this direction because this really allowed to treat, like realistic problem, not just model system. And then,
Dominika, can I ask a question?
Yes.
I'm always a bit confused about the terminology. It's always referred to as LDA plus DMFT. Now, why still LDA? Why not GGA plus DMFT or hybrid plus DMFT?
Okay, you could, I think it's historical. You could do something else, but see, the problem is that I think that the historical problem was that LDA was very cheap and hybrids were expensive. And also because, so you could do GGA. GGA is not much more expensive than LDA, right? I think that in LDA, they also could rationalize easily how the double counting should be subtracted. Not exactly, but like kind of, even the approximate description could have been expressed better than the other like hybrid levels and so on. To be honest, I also think that there is one more motivation, that they really wanted to have like a very low level method. The higher you go, the more sophisticated this hybrid is. It's very hard to kind of argue that, like, how should I correct, right? So you probably want to have like good method that describes this S and P electrons, but it has the D electrons not, correlated in major way, because you want to put that correlation by some high level method. But I really think that it's historical that mostly LDA was popular because LDA was very cheap to run. And even up to now, I think many of these codes for solids, very many people rather run GGA, LDA, or PBE. Like, probably the hybrid is not the first, choice. So I think it's really historical. But of course, there are problems, right, in this method. How do you evaluate the double counting? Because we have the exchange correlational functional, but it's impossible to many times split exchange and correlation exactly. So that was problematic. So one of the answers that is systematically improvable that got introduced, to remedy this situation, were basically methods called GW plus DMFT, and seen GW plus E DMFT, so E for extended DMFT. So usually these methods were written based on what is called psi functional. So this is a functional that is a functional of Green's function and screened interaction W. Like, you remember that the original Latinger functional was the functional of G and the bare interactions, not the screened interactions. So this was like an answer that was completely, in principle, systematically improvable, right? And I would say it was supposed to be superior to the GW plus DMFT. To Hartree-Fock plus DMFT. So see, one of the problems is that actually, due to many computational difficulties in all these approaches, what was happening, that actually the true guts behind what was happening was that one had a realistic system, one would map it to some sort of low energy model like 2D Hubbard. This model would be solved in a very controlled way, but would be solved with these effective interactions. So, and this mapping of the realistic system to this model system wasn't fully, this is only approximate, right? So that eventually became, I think, one of the huge problems in this sort of embedding calculations, that one wants to remove this type of approximate mapping and work really with the full problem explicitly. So why this is a problem? So just to show you, so this LDA plus DMFT was enormously successful. People treated like very, very many compounds and they were getting very good answer. But just to show you where this may become a problematic. So see, this is like some kind of compound of vanadium, basically. And you can see that depending on this effective U, you can get metal. You change a little bit this U, you're getting basically the band gap starts to open, right? U becomes a little bit bigger and it's insulator. So if really one wants to deliver completely material specific simulation, this is a problem because these parameters will adjust what we're seeing, right? So kind of we don't deliver a specific answer for a given material. Not necessarily always a problem, but in principle, this for many compounds, this may be a problem. So one of the things that we worked on is, is like also Green's function embedding theory, which we called self-energy embedding theory. So we rejected this sort of idea that it has to be done in this, that we have to have this, physically defined orbitals, like the d orbitals. They may be used, but don't need to be used. One can have any general weakly correlated and strongly correlated orbitals. So the functional was written basically as an approximation to the true Latinger word functional, where one has the total functional for the weakly correlated problem, right? And then some sub-functionals for the strongly correlated problem, and again, one subtract double counting. So what you can see that the functional is very similar to DMFT. In all these embedding methods, the major difference is how we define a procedure for evaluating of these pieces of functional. So from general functional point of view, when one writes the simple formula, everything looks the same. The kind of detail, like the devil is in the details, how these quantities are really evaluated within these different embedding methods, which are based on Green's function. So one can view this, right, like from kind of physical interpretation, that if we talk about set, the same would be true for DMFT. When the embedding is only done with Hartree-Fock, set reduces to DMFT. That basically you can think that in Hartree-Fock, each of these electrons would be embedded in a mean field, and in a correlated method, the strongly correlated electrons are embedded in some kind of correlated many-body field. Right, so basically this self-energy has to be evaluated in such a way that it accounts for this embedding. So in set, we had two different ways of writing this functional. We could have a functional with basically non-overlapping pieces coming from these different strongly correlated orbitals. We could also treat different strongly correlated orbitals with different pieces of the functional, so that resulted in some kind of many-body expansion of self-energy in the presence of this weak correlation. But basically, see, all these functional equations are very general, as I told you. That the difference is how people really in these different theories evaluate this phi strong and the double counting. So these are like the major mathematical differences. And in these theories, similarly actually to DFT, we also have to define an auxiliary system that we are solving. So in order to solve for this phi strong, we introduce this auxiliary system, which we call impurity problem. So see how this impurity problem arises, right? So we have this global intractable problem when we have a mapping onto which we try to map onto a simpler problem, which is this auxiliary problem. And usually this problem would be, like some sort of d orbitals embedded, or, for better or worse, one may think that we could embed the full unit cell in some sort of frequency-dependent field. So the hope of this mapping is such that basically the local Green's function of this lattice and local self-energy of this lattice can be mapped onto the local Green's function of this auxiliary impurity model or local self-energy. And here again, I want to stress that what I'm telling here would be the typical mapping for DMFT. For SET, this mapping is tiny bit different, but this is, again, details not essential, for general introduction to the problem. So we have this embedding mapping onto this auxiliary problem, right? And we would assume that the solution of this auxiliary problem would recover the quantities from this full lattice. So basically this frequency dependent potential, which is this embedding potential, is usually found self-consistently. And the hope is that the one-body properties and electronic energy of this unit cell are unchanged as a result of this mapping. So basically in DMFT, the embedding condition is that the lattice Green's function in the subset of the cell, so restricted only to that cell, would be the same as the Green's function of this basically auxiliary model, which would have right now, which would depend on the Hamiltonian of the fragment plus the Hamiltonian of the some sort of hopping between this fragment and the orbitals, which we call buff orbitals, plus the Hamiltonian of the buff. So, right, so the natural question that arises is how one finds this auxiliary model. So see how this auxiliary model is found, right? So the simplest problem that you can understand is how this model is found in Hartree-Fock. So see, this would be the full Fock matrix of the lattice, but I decided to choose here basically the Fock matrix of the cell as a reference point, right? So this is my Fock matrix of the cell. This is the interaction between the cell and the rest, and then that would be the Fock matrix of the rest. And right now I can try to prepare the Green's function of this lattice. So I prepared the Green's function just by inverting the Fock, right? Omega minus the Fock. And you can right now see that if I would try to basically evaluate the subset of this lattice Green's function, which is only in the orbitals of the cell, that would be my formula, right? I would have this term here, which is called hybridization arising. And this hybridization arises because basically the inverse of this G lattice, right, in the orbitals of the cell is not the same as basically the inverse only of the subset. So basically this hybridization is kind of describing for me how the cell is embedded, right, in the full problem. So I can then mathematically express what is this hybridization, right? So this hybridization is basically the Fock matrix of the interaction divided by omega minus Fock matrix of the rest times the Fock matrix of the interaction. And this hybridization accounts for all these, right, effects between really environment and this chosen cell. So it accounts for this electron exchange and the delocalization. And right now the problem is, right, how do we find a Hamiltonian that recovers this Green's function in the presence of this hybridization? So one of the simplest way, right, like what was originally shown in the DMFT, and for Hartree-Fock, one can show it kind of trivially, is that this auxiliary model, or this Hamiltonian, which is called Anderson impurity model Hamiltonian, would be the Hamiltonian of the cell plus the Hamiltonian of the interaction plus the Hamiltonian of the bath. And right now, the Hamiltonian of the cell is just regular one-body part of the regular Hamiltonian, right, in the cell. The two-body part, which are just the Coulomb interaction in the cell. And then we still need to find this Hamiltonian of the interaction and Hamiltonian of the bath. And what one can show that this one's, if one looks at this expression, right, for Hartree-Fock, would be basically this interaction between the chosen cell and the rest of the crystal, right? And this one fixes the energy level of the rest of the crystal, so that would be the Hamiltonian of the bath. In general case, for an infinite solid, see these sums here, which are over the rest, would extend to infinity. Okay, so one would need to have infinite number of bath orbitals and infinite number of interactions to basically express this, like to mimic the hybridization that is evaluated with this Anderson impurity model Hamiltonian. Usually what one does, one expresses this bath in a diagonal basis. So see, these are just energy levels, right, with value of this energy levels, right? So, and this is how the cell couples to the bath. But in practice, one also uses a small number of these bath orbitals. So in practice, one truncates this and one has like some tiny, usually quite tiny number, like maybe 4 or 5 bath orbitals per physical orbital that is in this unit cell. So, so consequently, this Hamiltonian that is solved by an accurate method is actually, has only few orbitals, because it has the orbitals of the cell plus these orbitals of the bath, but there are only a couple of bath orbitals per each of these orbitals of the cell. So that is regular part of the cell Hamiltonian, the interaction, and then one has the bath Hamiltonian. So see, one can show actually for many cases that really few of this bath, if that was like some sort of, I don't know, hydrogenic solid with one hydrogen per lattice edge, we could show that very few of these bath orbitals are necessary. So I have cut out a convergence with the bath from a paper of Ansgar-Leach, and you can see that basically with, like, these are the differences between the Green's function evaluated in very huge bath and small bath, and once one reaches 3 or 4, it looks pretty similar. So usually very few of these bath orbitals are necessary in order to express this auxiliary system. So the challenge is, right, that one has to evaluate the Green's function for this auxiliary model. So what is the challenge in condensed matter community, and the same I would say in quantum chemistry, is that one has to evaluate this for a general Hamiltonian that is here with general Coulomb interactions. So what can happen is, for example, in physics community, people use usually some kind of Monte Carlo, and this suffers from a severe sign problem when these realistic interactions are present in this cell Hamiltonian. However, chemists usually see this as a molecular Hamiltonian, so we use methods like, like RAS-CI or coupled cluster, and they can deal with usually not a large interaction strength, but they don't have a problem with completely general Coulomb interaction. So one can, for example, use RAS-CI, and, this can treat slightly larger impurity problems than, for example, exact diagonalization. So for 2D Hubbard model, you can see that as a function of basically excitations in this RAS-CI, this converges fairly well. All right, so back to the embedding. So see, the auxiliary problem is this impurity problem. And right, so in this different embedding method, this part of this strong functional can be evaluated a little bit differently, but each of them has to deal with this auxiliary problem in some way. And this auxiliary problem usually is like a problem of an orbital embedded in non-interacting buff, means some sort of buff expressed by one-body Hamiltonian. So what is happening in all this embedding calculation, that basically this intractable problem is split into a series of manageable calculations, right? So we have this low-level method for the whole problem, like GW, GF2, like some sort of low-level Green's function method, or Hartree-Fock. And then we have to evaluate this strongly correlated self-energy or functional, depending like what kind of method we talking about, for the small impurity problems, right? And these impurity problems really are a couple of orbitals usually embedded in a buff. So this can be done in parallel, also would have a lot of applications to quantum computing if only one could evaluate the Green's function successfully with quantum computer, because then, right, this part can be covered by quantum computation, while this part can be done completely classically. So what then one does is that this usually, in a physical problem, you don't even need to take the whole unit cell and embed it. That actually would be extremely wasteful, because these methods for evaluating the strongly correlated Green's function are extremely expensive. Usually one embeds a couple of orbitals. They may happen to be the d orbitals. They may happen to be some kind of hybridized orbital between d and p. They may usually lie near the Fermi level. So what one does, one separates this different energy scale, chooses the most important orbitals. One uses basically these different methods for evaluating the strongly and weakly correlated beat. One tries to be systematically improvable, so one tries not to have any empirical parameters. Historically, like LDA plus DMFT may have some parameters like U and J. It also may not have parameters depending how this U and J is obtained. They can sometimes obtain it from some constrained DFT, so often they don't adjust. So usually the goal would be to, at least for chemists, would be to maintain very high accuracy, include temperature, right, and calculate these quantities of interest. So, right, like for the small subset of strongly correlated orbital or this impurity, we usually use very accurate method, and we use some sort of approximate method for all the other remaining orbitals. So, how am I doing with time? Okay, maybe I skip. So I wanted to show some results, but maybe I can go very quickly through. So see, for example, for molecular problem, how would you do it, right? You evaluating the Green's function for the whole molecular problem. You usually would then choose some natural orbitals, which are the most important for the problem. You would embed them. You would evaluate hybridization between these orbitals and the rest, right? That was the delta of omega. You would express what are the orbital energies and interactions in order to fit this delta of omega. You would solve this impurity problem, evaluate this strongly correlated self-energy, and you would iterate. So for molecules, I can show you that, this embedding methods, for example, like SET, which is self-energy embedding theory, works very well. So it reaches comparable accuracy to full CI-QMC or DMRG for atoms or transition metal molecules. So despite this crude partitioning, because, in fact, we are like really choosing this orbital, we treating at one level, right? This at the other level, it's embedded, one can actually get very good accuracy. So I'll skip the other examples, and I have some example for solid to show you that it works well, but since here I'm supposed to only do tutorial, then I would say I talked about this other example during the second part of the workshop, that is more devoted to research. And right now I will just tell you that there are key features, right, for all these embedding methods. So the major goal is to change this intractable problem onto a series of manageable calculations that are performed at different levels. And that one can evaluate this self-energy at the low level with some sort of low-level theories like GF2 and GW. Basically, these are usually quite systematic approaches. Either one can increase the size of this problem, which we call impurity, which is auxiliary, or one can improve this theory that is treating the environment. So in principle, one can actually get very systematic convergence. That may not be always possible due to the computational cost, but in principle, it's systematically improvable. So these embedding theories, they avoid many problems that you have in, of more brute force method, like CASPP2, where, for example, your active space will suffer from this exponential growth as the number of strongly correlated atoms increases. Right here, that's not happening because the embedding is done local to the cell. We also don't have like a problem of ordering orbitals like the MRG. And in the case this embedding methods is done in Green's function, then one can recover both the spectroscopic quantities and energies. So I would want to thank my students for working on many of these interesting topics, and I would want to thank the funding agencies for funding, and thank you for listening. In case you have any questions, I'm very ready to answer. Thank you once more for inviting me.